Big O is a way to measure the efficiency of an algorithm. Say we want to find a target element in an array. We loop through the array and we print found whenever we find the target. How would you describe the efficiency of this algorithm? You could say it's pretty fast, but that's very subjective. It's the fastest possible algorithm that solves the problem. That gives us a lower bound, but doesn't speak to how fast it is. What if I just run and time it? This does give us an idea about its speed, but it's specific to the specs of my machine and doesn't translate to other machines. How about the bigger the input, the slower the algorithm? Now we link the efficiency of the algorithm with the input size, and this is what Big O aims to do. Big O is a standard way to describe the relationship between the runtime of an algorithm and the size of the input data that isn't coupled to any hardware spec. Let's look at some common time complexities. The input size is charted along the x-axis and it's charted against the time complexity of the algorithm. O1 or constant time is the fastest asymptotic runtime, where the size of the input has no effect on the runtime of the algorithm. For example, a function that takes no input to begin with, obviously there is no relationship between the input and the runtime. Next, we have ON, or linear time, where the runtime increases in proportion to the size of the input. For example, looping through an array and printing each item. When the input size is 3, we do 3 units of work. When the input size is 4, we do 4 units of work. When the input size is n, we do n units of work because, we're just printing the entire array. There is a linear relationship between the size of the input and the amount of work we do. So we say the runtime is O of n. O(n) squared time, or quadratic time, is where the runtime increases in proportion to the square of the input size. Now our code is printing out each pair of elements in the array, and due to this nested loop here, with an array of 3 elements, we do 9 units of work because there are 9 pairs in total, and the print statement is called 9 times. With 4 elements, there are 16 pairs, so we do 16 units of work. And with n elements, we do n squared units of work. The runtime increases at a quadratic rate as the input size increases, so the runtime is O of n squared. The terms big theta and big omega are used in academia, but not so much in industry. You may come across them in school though, so let's go through the terminology. Again, we are searching for a target element in an array. Big O describes the upper bound, that the algorithm won't be slower than. Well, we need to step through every item in the array, so an upper bound is O of n. It is also correct to say that the upper bound is O of n squared, since if it won't be slower than O of n, then obviously it also won't be slower than O of n squared. You could go on and say that the upper bound is On cubed or On to the power of 4 and so forth. It's probably not useful to say that, but it is correct. Big omega is the lower bound, a guarantee that the algorithm won't be faster than. We know that the algorithm won't be faster than omega of n since it needs to loop through the entire array. There's no way around that. It's also correct to say that it won't be faster than omega of 1 since obviously n is greater than 1 and our algorithm is slower than a constant time algorithm. Big theta is the type bound that guarantees the algorithm won't be faster or slower than. Well, we have our upper bounds and we have our lower bounds, and the type bound is theta of n, where the upper and lower bounds converge. So the definition of a type bound is the place where the upper bound and the lower bound converges. Tight bounds are the most useful since they give us the most precise description of the runtime of the algorithm. Now, a really important point to remember is that the industry use of big O actually correlates to big theta in academia. So in an interview, you would say that the runtime of this algorithm is big O of n. And of course, it's also correct to say that the runtime is theta of n, but this terminology is just not commonly used in industry, even though it is in academia. Now, one rule to follow when calculating big N is that we want to drop the constants. So we've already seen that this find algorithm has a runtime of O of n. And say we have another algorithm, find2. It loops through the array twice because it's looking for two different target elements. You might think that the runtime is O of 2n, right? Because there are two loops. Well, this is actually incorrect. The runtime is still O of n. Big O describes the rate of change in the algorithm as the input grows, and it's not meant to be a tally of the total number of instructions executed by the computer, even though counting these steps might help us reason about the time complexity. It follows from that rule that we also drop the non-dominant terms. We know from drop the constants that when we have n squared plus n squared, that simplifies to 2n squared, we drop the constant and it becomes O of n squared. So if we have n squared plus n, well, that's smaller than n squared plus n squared. And we can simplify that to O of n squared because we only keep the biggest variable, which is n squared. But note that it is still possible to have sums in the runtime. So for example, we have two different arrays and we're searching for the target element in both those arrays. So we need to iterate through array and array 2, looking for the targets. Now the runtime is O of n plus m, where n is the length of the first array and m is the length of the second array. This is because n and m are independent of each other. We don't know which one is bigger, so we can't simplify the runtime anymore. Now, let's talk about some limitations of big O. Big O is theoretical. It describes how the speed of the algorithm grows as the input size gets infinitely large. In practice, speed depends on things like your hardware specs and the nature of the input data, like whether there are any patterns in your data and the average size of your data. Sometimes a theoretically slower algorithm will be faster in practice based on for certain inputs. So for example, two common algorithms for finding a value in a sorted array are linear search, which runs in O of n time, and binary search, which runs in O of log n time, and so is asymptotically faster. But in practice, linear search actually runs faster on smaller inputs. So I benchmarked this on my computer. It was faster for about 100 elements, but this would vary based on the computer you're doing this test on. And the reason for this is because computers can better optimize for linear search. All Big O tells us is that the speed of linear search will increase faster than the speed of binary search. So at a sufficiently large input size, binary search will become faster. Now, the takeaway here is that Big O is a good starting point when choosing an algorithm, but you should run benchmarks for your specific input data. If you know that your input data is going to be small arrays, then well, obviously you should implement it with linear search because that would be faster in practice, even though binary search is theoretically faster and would be faster for a very large number of elements. Finally, I want to touch on space complexity, which is just Big O analysis for the amount of memory that an algorithm uses, because that is important as well. All the same concepts from time complexity apply here. For example, we have our find function. The space complexity is O of 1 because, well, it just creates a couple of pointers and it's going to create the same number of pointers regardless of the size of the input. So note here that we are not counting the memory taken up by the array in the find function because, well, we assign the ownership of that memory to whatever is calling the find function. We are only interested in the space taken by the find function itself. Now we have a function that creates an array and populates it based on the input. If the input size was 2, the output would be an array of 0 and 1, and the memory used is 2, which is the size of the array. If the input is 3, the output would be an array of 0, 1, 2, the memory taken is 3. And so if the input is n, the size of the output array would be n. And now the size of the output equals the input number, so we can say the space complexity is O of num. Now we have an algorithm to create a 2D array, and we populate it based on the specified length and the width. With a length of 2 and a width of 2, we get a 2D array of 4 elements. When the length is 2 and the width is 3, the array has a size of 6. And generally, when the length is n and the width is m, the 2D array contains n by m elements. So the input numbers here determine the dimensions of the array, so we say the space complexity is O of length times width. Now stay tuned for the next video where we'll deep dive into some examples of Big O analysis. Please like and subscribe if you found this useful. Thank you.